We are studying about the initial value problems. We now discuss about another useful uh, unlimited population growth model, a physical problem, and we will use initial value problem discussion. In the case of unlimited population growth model, the population means people, plants, animals, or bacteria, for example. This is in the mathematical sense. The population takes discrete values with respect to time mostly, and so it is a discontinuous function, but with the assumption that the population is very large, then the function becomes continuous. So we can use calculus for the population growth model, and our assumptions are that the reproduction rate is constant, and the fertility rate is constant, and at any time t the present population is y of t, the function, and rate of change of the population is dy over dt. But we use this law that the rate of change of the population is directly proportional to the population at present time. So dy over dt is equal to kyt. We finish the proportional sign and we place equal to, and k is constant. Now this is a simple problem, first order ordinary differential equation, and we again solve it by using the method of separable of variables, and we divide this equation by y. Dy over y is equal to k dt. Now we integrate this simple equation. Dy over y is equal to integral of k dt. The integration on the left hand side is very simple, that is in the form of logarithm. Logarithm of, this is logarithm of y, this is kt plus log of a. Because on left hand side the function is log of y, so the constant of integration is log of a for simplification, and we transfer log of a to the left side. Log of y minus log of a is equal to kt. Here we apply the rule of logarithm, that log of y minus log of a is equal to log y divided by a. This is equal to kt. We finish logarithm. Y divided by a is equal to exponential function e power kt. Y is equal to a e power kt. This is the model, unlimited population growth model. This is the solution. Now this is the general solution, and for the particular situation we can find the value of a, and the particular problem is solved. Now for example, suppose at time t is equal to 0 the population is y is equal to y naught, then this equation becomes y naught a e raised to power 0. E raised to power 0 is 1. So a is equal to y naught, and the equation then becomes, this is known, and y is equal to y naught e raised to power kt. This is the equation for this model, and we will use in different examples, but here we use one example. Suppose in the course of a given year the number of cases of a disease is reduced by 20%. If there are 10,000 cases today, how many years will it take to reduce the number to 1000? This is our problem, and we will use this model population growth model. That is basically initial value problem. Now here our model is y is equal to y naught e raised to power kt. Three unknowns in the model. Y naught is unknown, k is unknown, time is unknown, and for the solution we have to find all these. It is given that today if there are 10,000 cases today, this is the population, diseased people, sick people, ill people, those are 10,000 today initially. When time t is equal to 0, the initial population is 10,000. So y naught is equal to 10,000, and our equation number 1 becomes y is equal to 10,000 e raised to power kt. One of the unknown is determined. Now the equation 1 becomes this, and here we are left with two unknowns. In the original equation we have three unknowns, and applying the initial condition to the problem, we have found one unknown, that is y naught, the initial population, that is simply given in the problem, and so our equation 1 takes the form of equation 2, and in equation 2 we are left with two unknowns. Now the next condition is the rate of reduction of the cases per year is 20%. Every year 20% cases of the disease are reduced. The number of diseases reduced in a year is equal to 10,000 multiplied by 20 over 100, that is 2,000. So 2,000 cases, 20% disease reduction is per annum in the population of 10,000. 10,000 multiplied by 20 by 100, 2,000 patients are reduced. Then after 1 year, when time t is equal to 1 year, the number of cases is equal to 8,000. 10,000 minus 2,000, that is 8,000. From equation 2, y is equal to, put y is equal to, when time t is equal to 1. T is equal to 1, then y is equal to 8,000. Put t is equal to 1, y is equal to 8,000 in equation number 2. Y is equal to 8,000 and 10,000 e raised to power k. Now we divide 8,000 divided by 10,000 is equal to e raised to power k. The zeros are finished. 8 over 10 is equal to e raised to power k. E raised to power k is equal to 0.8, and finish e exponential, its reciprocal is logarithm, so k is equal to log of 0.8. And the third condition is that when y is equal to, we want to obtain the cases to 1,000. Initially it is 10,000, and the reduction rate is 20% per year, and we have to find the time when the sick population is 1,000. So y is equal to 1,000, and we are to find t. In this equation, put the value of k. Y is equal to 1,000. Y is equal to 1,000, and this is 10,000, and the value of k is the logarithm of 0.8, and t is unknown. We have to find t. Now this is from equation 2, and from the value of k. We divide by 10,000. 1,000 divided by 10,000 is equal to e logarithm of 0.8 t. Simplify the left hand side. We have 1 over 10 is equal to e log 0.8 t. This is 0.1 e logarithm of 0.8 t. On both sides we take logarithm of 0.1, and when we take logarithm on right hand side, e is finished, logarithm of 0.8 t, and t is equal to logarithm of 0.1 divided by logarithm of 0.8, and the time will be nearly 10.32 years, the required time. In our previous studies, we used one initial condition or two initial conditions, but here in the model there are three unknowns and we need three conditions to find the solution of the problem. This is very simple growth, population growth model, and we can solve many problems related to the population growth. Population growth means people, plants, animals, or bacteria, etc. For the first case we used this one, y is equal to, when time t is equal to 0, y is equal to 10,000, and we obtained the value of y naught. And the other condition is the reduction per year is 20%. We used this one and obtained the value of the second unknown, that is k. And next condition is to find the time when the cases, number of cases is equal to 1000. We obtain time, and the time is 10.32 years. Next, we also use the concept of initial value problems in radioactivity, very important notion in the nuclear physics. As you know, some atoms are unstable and can spontaneously emit mass or radiation. This process is called radioactivity, and because the mass is emitted and we spontaneously and continuously, so there is decay in the mass, original mass, and this phenomena is called radioactive decay. Law of radioactivity. The law of radioactivity states that the rate at which a radioactive element decays is proportional to the number of radioactive nuclei at present. In mathematical form, let at time t the number of radioactive nuclei is y. Rate of change of the radioactive element is dy over dt, and it is proportional to the number of radioactive nuclei at present, that is y. Rate of change is dy over dt, and it is proportional to the radioactive nuclei at present, that is y. So dy over dt is equal to minus ky. Dy over dt is proportional to y, and dy over dt is equal to minus ky. The negative sign, here k is positive, and the negative sign shows that y is decreasing because of the mass is emitting spontaneously. So the mass is decreasing. The original mass, the number is decreasing, so it is a negative sign. Now this is the same model as the population growth model, and with negative sign. We again solve it mathematically. This mathematical equation represents this law in this form, first order ordinary differential equation. And now we solve this problem using separation variable method. So dy over y, and this is minus k integral of dt, integral of dy over y. The integral of dy over y is logarithm of y. On the right hand side it is minus kt plus constant of integration log of a we transfer log of a to the left side. Log of y minus log of a is equal to minus kt. Here we apply the logarithm rule. Log of y minus log of a is equal to log of y over a is equal to minus kt. We finish logarithm on the left hand side, and when we finish logarithm on the left hand side, the right hand side becomes exponential, because log and exponential are reciprocal, inverse of each other. Y over a is equal to e raised to power minus kt, and we multiply by a, then y is equal to a e raised to power minus kt. This is again like the population growth model, suppose at with the exception of negative sign. Suppose at time t is equal to 0, radioactive nuclei are y is equal to y naught. When time t is equal to 0, y is equal to y naught. So y naught is equal to a e raised to power 0. A is equal to y naught. Then the equation becomes y is equal to y naught e raised to power minus kt. With the help of this solution, we can find half-life. This is another important notion related to the topic. Half-life, it is the time required for half of the radioactive nuclei present in the sample to decay. The remaining, which time from original quantity of the radioactive element to have half quantity. The time lapsed during this phenomena is called half-life. Suppose at t is equal to 0, radioactive nuclei are y is equal to y naught. The number y present at any later time t will be y is equal to y naught e raised to power minus kt, and we seek the time t is equal to capital T when the original when the quantity of the radioactive element is equal to half of the original. Original quantity is y naught, and at any time t, suppose the quantity is half of the original, y naught over 2. So the t is equal to capital T, and y is equal to y naught over 2. So then y naught over y, replace y naught over 2, and small t is equal to capital T. Then this equation becomes this one. Now cancelling y naught on both sides. When we cancel y naught on both sides, we get 1 by 2 is equal to e raised to power minus kt, and 1 by 2 is 0.5 is equal to e raised to power minus kt. We finish log e exponential, or we take logarithm on both sides. From here we take logarithm on both sides, logarithm of 1 by 2, and when we take logarithm on the right hand side, exponential function, exponential is finished. So logarithm of 1 by 2 is equal to minus kt. Interchange left and right hand sides, and finish the negative sign, that is kt is equal to minus logarithm of 1 by 2, 1 divided by 2. This negative sign becomes the power, and so this logarithm is reversed, and log, we get log 2, and we want to find the value of capital T. From here capital T is equal to log 2 divided by k. Half-life, this is half-life. T is equal to the formula of half-life, log of 2 divided by k, the constant half-life, and this is the value of k is related to different elements. This is the formula for half-life. And for example, for radon, the value of K is 0.18. 0.18. So the half-life of the element radon is equal to T log of 2 divided by 0.18, that is equal to 3.9 days nearly. And this is independent of the quantity, original quantity. The original quantity is more or less, it does not matter, but it will be half within in 3.9 days, more nearly 4 days. So these are the problems, different problems related to initial value problems and some boundary value cases also.